Hello, today we are presenting the Mars rover helicopter problem, which is project 1 in Physics 211 for us. My name is Quince Nye.
My name is Gordon McCrickard.
My name is Abdullah Husainan.
And we will just get right into it. We are each presenting a different portion of the presentation, and start with the problem statement. So we have been given the problem statement on the top right, which is a helicopter for the next Mars rover. The helicopter is designed to launch from rest at a negative time constant t, after which it flies for some time before landing a known distance d away. T is an unknown but constant time, and there are two more constants, alpha and beta, which are known constants. So they will be set by us, and we will be solving for how long the helicopter is in the air, as well as how far away it lands, and trying to describe the motion of the helicopter. I have created a smaller illustration below the problem statement, just detailing the basics of that. We've been given the equation for acceleration, but we can't really get much out of that. So to get any useful information, we have to integrate the acceleration equation as we learned in class to get the velocity with respect to time function. And integrating that again, we can get our position with respect to time, r of t. So with description of motion, we know that it starts at negative t, meaning that the time constant is negative, which will definitely change the way that the motion is displayed, since negative time is not a real concept, but we can still show it graphically. And we can see in the equation that there are two components, x hat and y hat. So we have an x component and a y component, and it's in the two-dimensional plane. And solving for t, we were able to find that it is mostly dependent on the constants alpha and beta, which are tied to the y direction and x direction. And later on, it'll become clear why we decided the alpha and beta must be constants of acceleration in each of these directions. This graph displayed is the graph of the acceleration. And we used the Desmos graphing tool to show it because it was hard to make any sense of it without from just the equation. And in Desmos, we were able to use sliders because while alpha and beta are known constants, they still weren't given to us. So don't pay no attention to that beta and alpha and c. Those are just the constants I chose because I had already defined the other constants, but they are beta, alpha, and big T. And if you look at the graph on the right, you can see that the acceleration of the helicopter will follow a smooth curve where the acceleration is initially increasing until a little after 2, which remember is relative because as we change the time constant, the whole graph will get wider, the range will increase as well as the domain. But a little after 2 at this time constant, the acceleration starts decreasing, but it's still accelerating at a slower rate until it crosses the 0 and becomes negative, which at this point, the helicopter is decelerating. And the area where the acceleration graph crosses the motion graph, which we will show the motion graph later, that'll be where it actually lands at a deceleration. All right.
So this is our topic on sense making. Remember the helicopter launches at little t equals negative big T. Using that, as well as using our understanding of initial time, we are able to convert the instances of little t into instances of larger t, which helps simplify the equation. We know the distance the helicopter flies horizontally is d, and t is an unknown but constant. From there, we're able to get alpha and beta are known constants, but not defined. We are looking for the velocity with respect to time and position with respect to time. We're assuming the helicopter is moving in 2 dimensions, with positive y being up and positive x being to the right. We can also assume that the equation is representing the entirety of the movement, but can also include initial position if we wanted to, but for our purposes, we assumed the initial position and initial velocity were 0. To solve this problem, we looked at movement over time. We're also looking at velocity. This involves an equation with respect to time, as well as using unknown variables. Using integration first and then simplifying, we're able to find delta x and delta y with respect to our t value. From here, we can find t by substituting what we know into other equations to find the one missing t. You can see this in the equation on the right-hand side of the screen, where we solve for delta x, delta y, t squared, and then finally simplified to just capital T, which is in terms of d and beta, which are 2 known constants. As we moved from acceleration to velocity and from velocity to position, we lost a second squared in the denominator of each unit at each step. This leaves velocity in meters per second and position at meters. This is where we want both of them. The way the helicopter is undergoing its movement makes sense in context. We can see that there's no jerking motions or breaks in the graph that are inconsistent with what the equation is representing. The direction we can see from the motion graph is consistently forward without any spikes in the position that would be harder to explain in the context of this problem. By looking at the different estimations of what is known but constant variables could be, we got to understand their impact on the equation. We tried large and small variables for alpha and beta that we thought reasonably represented the way they changed the graph. We conclude the helicopter takes off upward and moves the distance horizontally equal to d. It then lands higher than it started.
All right, so this question that we did is pretty much similar to the Mario question that we did in the class, where they both have the x hat and the y hat. Also, they all started with the acceleration and took an integral of the acceleration to get the velocity. And to get the position, we take the integral of the velocity, and that's why both were so similar to each other. And why was this problem different from the previous ones? Because this problem had a negative value of the time limit of the flight, which is something we have not been confronted with before and added more complexity. We have done sense making on similar problems, but with a more complex acceleration equation. And the sense making was at a different level.
And just to add another reason that it was different was that in previous problems we've known the path of the projectile, and that made it a little more easy to do the sense making, like in the Mario problem, where in this one we had to first figure out the path of the projectile to even understand what we were looking at. All right, that kind of brings us to conclusion here. And we have put the position graphs in the conclusion, which don't make a ton of sense at first. But once we understand that the time constant is negative and that will create a mirror image of the graph on the right, it makes a little more sense. Just analyzing the graph on the right, the position as the helicopter goes along, it flies higher, increasing in acceleration upwards. But it does not actually return to the ground, as we previously stated, meaning that the helicopter, based off the equation of acceleration, must have landed at a higher level than it started. Other than that, I believe this problem was a good way to tie together a lot of the tools and skill sets that we've been building in our homework problems, as well as the in-class problems, and made us use them sequentially all at once. And I guess hopefully it helps arm us for project 2, where we will have to derive the solutions ourselves and make a new video. Would say questions, but this is a video. If it's presented in class, then questions can be asked now.
All right, thank you.
All right, thank you.